Good morning, everyone. Nice to chat. Welcome to Thursday of week 3. I guess, we're nearly a third of the way through the term once we get past the lectures today. Good morning to all the people up early. Any of our friends from Asia, super early good morning to you. And we'll try and make today, kind of light and fun and all of that. There's not a ton of time pressure on us today. What we're going to be doing today is we're going to be going through two lectures, 3.4 and 3.5. It's all about testing. It's like kind of a continuation on from the linting stuff we were doing yesterday. It's really just an expansion of that whole topic. And if we have extra time, we're going to go do maybe next week's topic early, but we'll see how we go. Depends, because we changed again some slides around, so who knows how long some of this stuff will give or take 5 or 10 minutes here. But let's get stuck into it. So while we're on this SDLC testing topic, it's important to continue to take a step back and understand what testing is, because hopefully you're probably going to be writing tests for the rest of your life, right? But what you need to understand, I guess, is how all these pieces fit together. So, why we test, conceptually, what things we test. These all fall into a broad bucket of what we call verification, which is what we're going to mainly be talking about. But we're also going to be talking about validation as well at the start, because we do have a few kind of big concepts here around what static verification is, dynamic verification, and validation. So let's try and first contrast verification and validation. So if you look up, some ISO standards, some international, cooperation standards, you'll see two definitions. One is, the definition for verification, which says the verification in a system lifecycle context. So think of that like, say the software development lifecycle. It's just saying a system is a set of activities that compares a product of the system against the required characteristics of that product, right? So that sounds a lot like testing. It's like we're comparing we're comparing a product against the required characteristics. And you can start to get a sense of this. Like if you think about your project, with your project, your PyTester just testing a system against desired characteristics. And this may include, but is not limited to, specified requirements, like an API or an interface, design description, and the system itself. It's literally like trying to say, does your system behave as you expect? Validation, on the other hand, is a set of activities that ensures and gains confidence that a system is able to accomplish its intended use, goals, and objectives. Now, you might be thinking like, okay, so what's the difference there between these two? Well, the one on the left is saying we're going to check a product against its required characteristics, and the one on the right is saying we're going to check a product to see if it accomplishes its intended use, goals, and objectives. Where this leaves us is essentially a simplified definition and a nice little way to contrast these, which is to say that verification is the topic of ensuring that the system has been built right, and validation is the topic of making sure that the right system has been built. So a little bit of a play on words there, but you kind of have to imagine, this is how I think about it at least, is that, someone comes along to you and says, we have a problem. The problem is that we don't have a mechanism to effectively communicate between UNSW staff. Okay, so there's like your problem. Then someone says, oh, I have a solution for that problem. We're going to build, this UNSW Streams app. We're going to build a UNSW Streams app, and it's going to have all these features, right? So, you have problem and then you have solution. And what verification does is after you describe that solution, think of like section 6 in the project with your interface table. Once you describe that solution, it's really about, has the code you've written, has the software you've written actually been built the right ways? And has it been built right with respect to the standards, the specification, the rules you set out? So it's very much like, this defines the correct system. Does your code build a correct system? Then on the flip side, though, validation is actually like kind of taking that a step above and saying, okay, well, you might have written some software and that software might have been built correctly according to the system, but did it actually like solve the problem? Was the right software actually built. So it's really taking a step back and looking at, what that, how to put it, what that overall goal is of the whole software, because you actually kind of get this problem, and I mean, I'll mention this now because it's really useful to think about in week 8, in week 7, when we actually talk about requirements. So I'll just jump ahead on it now because it's interesting. But there's this concept called the XY problem, which I know a handful of you have heard about, but most of you probably haven't, I would guess, just given the size of the course. There's a great there's a great Stack Exchange article on it, but essentially, I saved that up on a different screen, sorry. Forget you can't see every screen. So XY problem is basically a concept that describes you trying to optimize or overfit to a solution instead of thinking about the problem, right? So there's some descriptions of it here. XY problem is asking about your attempted solution rather than your actual problem. That is, you are trying to solve problem X and you think solution Y will work, but instead of asking about X when you run into trouble, you ask about Y. Now you can broaden this concept to a whole bunch of industries, right? This one is very specific to computer science. I deal with it a lot in the world of, startup spaces, but it's all the same thing. It's being a bit too solution oriented in your approach. And the example I tend to give students, because it's a really simple one that makes sense and hopefully can convey the point, is that if you say, let's say you what's the one I go to? Yeah, the one I go to is like, let's say you come to campus, which I know many of you haven't had the experience of doing, but like whatever it is, high school, friends, a park or something, and you come and your friends have got lunch, and you've come along with lunch too. You've got it, you've got your like lunch box. It's got some nice like massaman curry or something in it, and you're like, oh great, and then you realize you forgot utensils. You're like, oh god, I forgot to, I have nothing to eat this with. So you turn to your friend, and instead of talking about the problem, which is that you don't have utensils, you start talking about B, the solution, which is say finding like a fork or something. So you say to your friend, oh hey, do you have a fork? That's how you start the conversation. Do you say, do you have a fork? Your friend says, no, I don't have a fork. And you go, oh damn it, we need to find a fork. And then you start walking around. You start, maybe if you're on campus, you start, going into little shops and just saying, do you have a spare fork? Otherwise, you might go and look for a place you can buy one or something like this. And you might look around for half an hour. You might, be digging, and your friend's like, I'm hungry, and you're like, I'm hungry, but I can't find any forks. And then you finally sit down with, say, a fork, and, your friend's like, oh, what was that? What was the fork for or something? Not they would ask that earlier normally. But you say, it's to eat my food with. And they say, well, I've had chopsticks in my bag the whole time, and you're like, oh, I didn't realize. And like, what you end up doing there is you end up wasting all this time trying to find a fork, when in actual fact, you're not actually trying to find a fork. That is a solution to a problem you have, right? And you've been trying to produce the solution, but in actual fact, the problem you're dealing with is that you don't have a utensil to eat your food with. So if you actually start the conversation with, hey, I don't have a utensil, can you help me out? Yeah, turns out the food is soup. Can you help me out? Then it's like someone has a broader understanding of the problem. They can actually see if it's been solved correctly. The reason I talk about that is because the difference between a problem and a solution is a really important nuance that I don't think, in my experience, that at this point in your degree, you've probably had a great opportunity to kind of think about that in the software landscape. But I mean this sincerely. Up until this point in the course, out of everything we've talked about, at a personal level, me to you, if I was to say, remember one thing from the course, it would just be this. Because this is everything in life, honestly. Like, this is everything from writing code to human relationships. It's like, if you get too caught up trying to optimize or solve for solutions instead of thinking about the underlying problem, you get lost in the weeds. And the reason I mention this stuff is, well, I mean, let me just finish this. It's like, I would deal with this kind of thing every day. And this happens a lot with software. Like another good example, someone says, hey, how do I find a library to, convert strings to emojis? Okay. So you might think that's the problem to solve, but it's like, that's not actually a problem to solve, because you're probably trying to, you know, produce that solution, converting strings to emojis, because of some other problem you have, and that other problem might be, oh, you know, blah 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 blah. So it's like, even in the software space, it's really important just you as a team member expressing things, you as another team member listening to things, that you're always asking yourself, are we dealing with the problem right now? Because if we're not, we're going to get lost, and we're going to find suboptimal solutions. We're gonna hit, you know, we're gonna optimize a local solution that is just not ideal. So, you know, keep asking yourself, you know, start with the problem, all of that. You know, me and my friend have a joke where we refer to it as like getting out of solution mode. It's kind of what we would refer to it in the startup space. You know, someone comes along and says, "Hey, we really need this on a web page," and you say, "Okay, like why?" And they're like, you know, it's like, "Stop! You've actually just come to me and said, how do we implement this solution?" It's like, no, what's the problem? Well, it says, "How do you know when solution Y is the actual solution, but you're stuck on it? How do you realize whether you need to focus on X or Y?" I mean, you just ask yourself the why question. There's a point where you have to stop, naturally. You can't just keep asking why forever. But yeah, it's pretty much just along the lines of, okay, why am I doing this? I sit down and I say, all right, I'm going to make a lecture about linting. It's like, why? Like, what problem are we trying to solve with linting? And I mean, in a lot of ways, like, you know, the slides we put at the start of the lecture here are really trying to solve that problem, because, you know, the saying, okay, what's the aim of today? The aim of today is to teach verification, validation, and static and dynamic verification. It's like, okay, but that's just an outcome. Like, that's like, why are you doing that? And it's like, well, you're doing that because if you can't get a sense of what the broad world of testing is, then you're not going to be able to fit pieces together. Like, okay, well, there's the problem. That's what we're trying to check. So, you know, back to the slides around validation, the system, you know, verifications that the system has been built right and validations that the right system has been built. You know, to answer the question, was the system built right, would be on this lecture slide even, forget software for a second, did we teach verification, validation, and the difference between static and dynamic verification? Probably yes. So it's, you know, we verified that the system has been built right. But then the bigger question is validation. Has the right system been built? That's where sometimes you need to take a step back. You need to either look like at a higher solution or something broader, or look at like the problem you're trying to solve. And in this case, the problem we're trying to solve is understanding the concepts of testing. It's a very bad why here, but a very uninteresting why. But it's like, that's the kind of question you ask. So you say, all right, well, we can see the system's been built. The lecture slides do have this, they do have that, they do have this, tick, tick, tick. But was it the right, you know, what is it? Has it, you know, has the right system been built? Are these actually the things that help you solve the problem? You know, are these actually the things that make you go, oh, I do have a concept of testing? So it is important to contrast this notion of verification and validation, because they are just two different things. And typically verification is a lot of heavy software coding, not all of it, but validation is sometimes a little bit more just, you know, bring it back to the people who asked for it and be like, does this solve your problem? Because you could have understood their problem, been like, we're going to go build this. They say, okay, you go and build it correctly, passes all your PI tests, say, then you take it back to the person and you say, here you go, and they're like, that didn't really solve my problem. It's missing stuff. You've built the wrong thing correctly, right? So good verification, bad validation, to summarize, is, you know, you build the wrong thing correctly. You know, and that's kind of just a way to think about it. But let me get on from this. I've been talking a lot. In terms of verification, which is where we're going to focus most on today, right? So, you know, we've said verification, validation. Validation we actually talk a bit more about in week 7. We talk about use cases and other stuff. We're going to talk all about verification today, pretty much. Kaushik says, so PyTest is basically verification. Yes, exactly. PyTest is verification. And Waleed says, so things like beta testing, feedback rounds, part of validation. Depends what you're doing with them. I'll contrast that when we talk about it in a sec. Hopefully answer your question. Okay, so verification types. Verifying. Verification can be broken up into two main types of verification. The first one is static verification, which is what you know as linting. We talked about this yesterday, right? It's all the stuff around, type checking, style checking, logic checking, blah, blah, blah. It's static again because the code's not running. It's kind of like inspecting a car before it drives. There's certain, when we, I'm going to tell you some stories in the next few weeks about SunSwift, the solar car team at UNSW. And when you actually go and check if the car works, you actually, and this is true for many things, you actually literally go through two whole periods that they call, static scrutineering and dynamic scrutineering, and they test different things. Static scrutineering is like, how long's the car? Does it have this kind of space? It's a lot of measuring tapes. It's a lot of looking and taking notes and counting and inspecting, but the car's not moving. And then dynamic scrutineering is like, all right, let's drive it now. Let's test the brakes. Let's test the steering. Let's test how hard it can corner. You're actually seeing the system in action doing things. So static verification is all the linting stuff because the code isn't being run, whereas dynamic verification is kind of what you understand as testing. Like when I say testing to you, can you test your code? You don't think, oh, I'm going to lint it. You think, I'm going to run it under a various number of conditions and I'm going to see what its output is and see if it does what I expect. So generally speaking, in this world of static verification and dynamic verification, we kind of like static verification a lot in terms of the more you can do statically, the better. And in this magical ideal world, in this magical world, you could test everything statically, right? Some languages you can nearly do that perfectly. Other languages are just like impossible. But the more you can gain assurances that you've verified your software. The more you can gain assurances that you've verified your software before it has to be run, the better. And the reason for that is that, how would you put it? It's like compilers. Like compiler errors are easier to see. They're less likely to cause problems. They're easier to test. And there are certain languages, that have better static verification. Again, like C obviously has better static verification than Python. But a big part of that is the type system in C, right? So languages with types certainly are easier to statically verify. We're going to talk about types and type checking as like a bonus topic in like week 9 or something much later in the course. It's not really a big concern for now. But anyway, we like to do static verification. Now, in terms of static verification, I just want to expand this topic a little bit more because yesterday we talked about linting, and when I said like static verification is linting, it's not so much that linting is static verification, it's like linting is a form of static verification. In fact, style checking is a form of, static verification. So we're broadening the concepts here. We talk about linting yesterday, which is a form of a bigger bucket of static verification. We're going to talk about dynamic verification next, which is all part of a topic on verification, which is making sure that you built the system right. And that's all a big bubble next to our validation topic, which is making sure that the right system has been built. So when we look at static verification up here, you have the things we talked about yesterday, like style checking, type checking, logic checking, unused variables, usage before they're defined and stuff like that. However, there's actually even more you can go into depth with in the topic of, on the topic of static verification. And a few things we have here are key metric checking. This is something we're going to literally talk about today a little bit. We're going to talk about code coverage today, coupling, cyclomatic complexity. We talk about maybe 4 or 5 weeks. They're all ways to look at your software and ask yourself, do we think it's being built right? And what's a really easy key metric check? When we say key metrics, all we really mean is like a quantitative way to look at your code quantitatively and say, is this behaving? So an example that we're going to talk about today is code coverage, which is you can actually look at how much your tests are testing as a number, like PyLint, right? Coupling is how much is your code kind of interweaved, and is how sensitive is your code to breaking? How many imports do you have going all over the place? Is it a nice organized, system, or is it a giant web of a mess? Cyclomatic complexity we talk about later, which is like how many if and else statements do you have in a given function? Like how complex are your functions? Let's reduce it to a number. Let's actually say your function is like level 6 complex. You could do things like, metric check could be what's the length of your function? What's the average function length in terms of lines of code? Maybe that should be less than 50. That's a key metric check, and it can be done statically because your code doesn't need to run. And there's actually there's a whole world of these things well beyond my knowledge. There's like dozens and dozens and dozens of different kinds of things you can check with metrics against. These are just some of the ones we go through in the course. So this is one thing we didn't talk about yesterday because it's not part of linting specifically. It's often something that you might do separately, but it's still static. And then the last two topics which we don't cover, so we just want to, when we say they're not covered, it means we don't really go into any depth in them. So just talk about these very briefly, which is that we have formal verification and informal reasoning. Now, informal reasoning is not an internationally accepted term. That's actually just what I've called it here. But we're going to talk about what those two types of software verification are. And in most cases, they're actually quite manual because, these things, this kind of stuff is done by tools that looks at code quantitatively. This kind of stuff is done by linters typically. Or, type checking might be done as a separate. This isn't super rigid. These are just, these are all static concepts. Blake says, before we go to the formal and informal, what is anti-pattern detection? So, patterns is a software concept. I think we're probably going to talk about those briefly in week 5, but patterns as a software concept is really, a kind of standard best practice way to approach a problem. Like what are some examples in your own life where you tend to follow a pattern or a little mini ritual to solve a problem because it works? Like if anyone has any ideas, like where would you say there's a pattern in your own life that you use to be successful or solve a problem? That's my open-ended question to everyone. Turning it off and on again when the internet dies. Yeah, okay, that's one. Sure, yeah, it's like, okay, you have a problem to solve. You're like, okay, the solution here is, the restart pattern. You're like, I'm going to follow this pattern of behavior because I know it works. And we see this a lot in software. It's hard to get into the specifics because a lot of talking about patterns is very technical sometimes. Put in rice, I don't know what you mean, like washing rice, like the washing rice pattern or something. I mean, maybe we can stick with that. It's like, a pattern is like a blueprint for, good software. And in the software world, we have lots of patterns that we follow. Like, we can build software by composing other pieces of software. We can build software by building abstractions and using there's a whole thing on this that we won't go into now, but there's lots of approaches you can take, right? I'll give you some of the best. I'm often surprised how turning it off and on works for everything. Yeah, a big part of that's because software can be truly reset though. Like if you had a car and it wasn't behaving and you could just destroy it and get a new one, it would probably fix some problems, right? And software's this magical world that's all just magic. So but let's go to patterns. So for example, let's think of a pattern. Let's call it the for range pattern. It's really simple. So in Python, as you know, you have your kind of old style C loops. So I'll just answer this anti-pattern question. You might have your for I in range, length of list. And then you also have your, and then print list I. And then you also have your for item in list, print item. Now let's for a second just call the second, let's call the usage of this the for range pattern. I can call it, I'm just making that up, right? It's a particular general principle or process or behavior to follow that is generally deemed like a good way to, a good part of a solution. So why do we like the for range pattern here? We like it because, it removes unnecessary indexes, it cleans up the look of the code, very simple reason to do it. So when we talk about things like here, anti-pattern detection, if you remember yesterday, it actually told us, for instance, it was like, hey, you should consider using enumerate. That is what, like, I would consider here to be an example of anti-pattern detection. Your code, maybe the style's fine. There are no warnings. It's not potentially errorsome. It's just not maybe the right approach, in the sense that it's not a good pattern to follow. Maybe there are better patterns of programming. Maybe there are better, behaviors or habits or common processes to follow. So often in the software space, you'll hear about the phrase anti-pattern, which is often just a very, fancy way to say, this looks like bad software. This looks like a bad approach. So if someone showed you this, and if you showed someone this and they turned to you and they said, oh, that looks a bit like an anti-pattern, that's basically them saying, that looks like something that isn't following, a good software pattern, isn't following like a good, software habit or something like this. It's quite literally saying that looks like the wrong approach. That looks like a non-standard approach or something, a bad approach that could be written better, and everyone will understand why. There's a good reason why, but we haven't done that, so we call that, an anti-pattern here. That's what like anti-pattern detection is. Typically, it's like linters can do it. They're like, yep, as I said, good style, no warnings, but maybe that's not the best approach here. So basically, if something's not following convention, that's a good summary of it. The only thing I guess I want to be kind of clear on is that patterns aren't really like a convention like PEP8 or something. Like PEP8 is like a style guide. It's like, that's like the convention. Patterns are just like using for loops or while loops. Like, it's just a, we can use the word convention, but I think convention can sometimes imply like the way to do it. Whereas like often in this space, there's kind of like a handful of good approaches or good certain patterns, funnily enough, that you could apply to solve a big given problem. Now, anyway, let's get on to formal and informal verification. So formal verification is an interesting topic that you will probably largely stay away from in your programming degree, but if you're interested in it, you should definitely get sucked into it. So formal verification is a form of static verification that proves that a piece of software you've written is correct and has desirable properties in its entirety. And what you actually typically do is you take software or any of the code, algorithms, data structures, and you reduce them to mathematical objects that you can reason about. And this is like a very intense field that I have very little understanding of. But it's essentially like, if you imagine for a second, you get your program, you reduce it to math or, mathematical objects, and then you prove it's true like you would in a math course where you're like, prove that, I is always less than 6 or something like that. You write out a proof for it. So it's super mathematical, super mathematical. But it's interesting. And the reason it's interesting, it's very interesting at UNSW in particular, right? Because we have oh no, they removed the page on me. There's a Data61 group at UNSW who developed the Cell 4 kernel, microkernel, which is literally like a mini operating system. Oh, that's why it's not working. Okay, sure. It's a mini operating system. You can Google this in your own time. But what they did, and what was so kind of profound about this, 4161, that's right, thank you. I forgot the course code. So there's actually a whole course on this. Advanced topics in software verification. I haven't done this course. I haven't done this course. I don't really know how many people have. I don't know many people that have done it myself. But yeah, this course is about mechanical proof assistants, how they work, blah, blah, blah. Higher order logic, natural deduction, lambda calculus, tell me right. It's a computing course about math, and it's about reasoning programs with math. Now, here's the trade-off with formal verification. The plus side is that if you can formally verify code, there's really nothing else in the world that I understand that can actually prove code is correct. The The downside though is it's really cumbersome. So even in the example of the cell4 microkernel, it was a 10,000 line piece of code in C, right? But to actually expand it, they ended up writing nearly 500,000 lines of proof script, as in like the math that was written to prove it was correct was like 500,000 lines of code, and it took it took 20 person years. So as in it took 40 people 6 months of full-time work. It's like how you could imagine it. And what's interesting about this though, and I'm just going to jump ahead to this slide, is that typically when we talk about verification, generally, like some of these words are being thrown around here, but let's just talk about verification as testing or something. I'll replace that word testing with verification. It's like verification shows the presence, not the absence of bugs. And this is really important because when you think about testing and we say cover all your tests, make sure you've tested everything, what's really happening there is you are just looking for bugs. You're not trying to prove there are no bugs. It's very difficult to prove there are no bugs, because how can you prove to me that there's no bugs? We say I've written some tests, and you say, yeah, but tests are looking for bugs. They're not demonstrating the absence of bugs, right? So, yeah, that's why formal methods and formal verification is really interesting, because all other types of static verification, dynamic verification are often just looking for bugs. And the more tests you write, you're looking for more bugs, because the more bugs you find, the less other bugs you've probably missed. And nearly all software is buggy, because formal verification is really expensive. But it's certainly interesting. And, the reason this was exciting was, if my memory serves me correctly, when they produced the cell4 microkernel, it was the first provably safe kernel, provably correct kernel ever. Which meant that they literally developed an operating system that worked in the most literal sense of the word. Not like we've tested it exhaustively and we're going to patch bugs every few months when we find them, like Microsoft or Apple or something. But it was like, it works. It just works. We've proven it mathematically that it's bug free, kind of thing. Now there is another course as well, COMP1531, about this, called Informal Methods. It's a great course. It's run by Carol Morgan, who's most people running some of these courses are very, very smart. Informal methods are practical structuring and design techniques which encourage programming that is easy to maintain or understand. Blah, blah, blah. I have a bunch of people who've done this course and they said it was challenging, but they loved it. And this one kind of delves into not just let's do formal methods because there's already a course on that, but it's like, what are some other ways that we can actually verify software? So, if you are interested in this whole verification topic, then these are cool courses to spend some time looking into. The last point I want to point out, though, in terms of our list of static verification, is this idea of informal reasoning. Now, again, I just don't mix this up with the course Informal Methods. But the reason I wanted to point this one out is it's actually relatively common in the software space to want to build habits, not just in using tools, but to actually looking at software and reasoning with software. As in, you'll notice this with your tutors, right? Really simple. You'll write some code that doesn't work. Your tutor looks at some code and says, there's the problem, right? And that's not just because they have a little computer in their brain that looks for bugs. That's because they look at your software and they think, all right, well, we have an if statement and an else statement. So they're actually thinking about it. And there's nothing to teach on this topic. It's actually just saying that don't underestimate the experience that you get from writing lots of software and just looking at lots of software and debugging lots of software, because just being able to kind of visually check things out is super useful. Particularly if you're not being paid to write tests in some situations. And also, one reason we like good software design and why we like type checking and style checking and logic checking is it makes it easier to reason with code, to look at code and be like, what's going on here, to follow the flow. That's why and that's another part of why we want you to write good code, because it's not just that it's more likely to work and it's easier for other people to read, but it's going to be easier for you to kind of look at and test in your head, for lack of a better phrase. Testing in your head is not a scalable, reliable way to test, but it is just a reality of, not all code that's written is tested. with actual testing systems. So being able to make sense of it's really important. Masoni says, I was wondering, do people even have a need for formal verification in the industry? People doing it. It seems quite niche. There's not a massive demand for it because it's expensive. You know, like businesses... I remember, I was talking to a colleague the other day, and I was like, we were talking about some software design, and they were saying that, we got to build some software that does something with some money. And I said, I don't know how to. I'm really worried. I don't know how to make it work. Like we can test it, but like, what if it fails or something? And he was basically like, we don't need to make it perfect because I know that's impossible. We just need to make it perfect enough that when something goes wrong, it's so unlikely that we can deal with it or insurance can deal with it or something. And I was like, oh, okay, that's a good point. Everything we do in software isn't about getting it perfect a lot of the time. It's about getting it like as good as it can be. So, most companies and stuff, they know there are going to be bugs in their software. And they could probably triple, quadruple their budgets to fix everything or to, formally verify everything. But which is cheaper, to kind of like have massive scale ups in budgets, or to just have teams that respond to problems if the problems are really small, So the question around formal verification is often very much a business decision. Like, what is the best way to, to actually meaningfully test something to the limits we need it to be? Because nothing's bug-free, right? I mean, there's some bug-free things, of course, but most even reliable software you use is bug-prone. There's a reason that they don't formally verify everything. Okay, so let's get on to dynamic verification. Dynamic verification is verification that's performed when you're executing the software. You're actually running it. So you actually write Python 3 something. It's PyTest, right? So PyTest is all forms of dynamic verification. If the code is being run while it's tested, it is dynamically verified. Now, for the sake of this course, we're going to break up dynamic verification into 3 kind of buckets. You have testing in the small, as in small tests. You have testing in the large tests, and then you have acceptance tests. And you might find different names for these around, but conceptually they all fall into this rough category. So let's go through them. Testing in the small, dynamic verification. Testing in the small is generally what we use to refer to unit tests, which the ISTBQB, it's one of those international bodies again, refers to as testing of individual software components. Now, most literally, you can typically interpret this as functions. So when someone says, I'm going to write some unit tests, quite often they're saying, I'm going to test that my function works. When they say unit test, unit means one, it often also means that you're going to test that your function actually, what would you say? That your function actually, trying to think, how would you describe it? Your function is tested by itself in isolation of everything else. It doesn't know any other functions exist. It's just by itself. Now, you aren't actually doing a ton of these in your project, and we're going to go through examples maybe after we talk about the 3 types, because that'll be easier to piece them all together. But typically, unit tests, which are just testing a function, typically, these can either be white box tests, which means they break abstraction and are aware of implementation details, or black box, which means they don't break abstraction and aren't aware of implementation details. And it's often written by engineers who will implement the work, right? Pretty simple. Testing in the large is actually starting to test software, looking at it from a bigger picture. Because, as you get from small testing to large testing, you start off being like, I'm testing this function, and then suddenly later on you're testing the entire software system. However, there's some steps in the meantime. So larger tests are tests that are performed to expose defects in interfaces and interactions between integrated components. It's basically saying, does your software work together? And you can probably understand this one quite clearly because this is what's happening with your project. You have all these different units like auth register, auth login, or you could treat that as a unit, depends how you conceptualize it. Do they work? Do that work with channels? Does that work with, messages? Like, do these things work together? So testing in the large is about looking at many parts of a system and trying to test them all together. And these are typically black box tests, like your project, where you're actually going and writing stuff without worrying about implementation details. And the reason for that is because trying to write these bigger tests with all these components together and then actually break abstraction creates really fragile tests, because now it's testing a ton of stuff and a ton of its implementation specific. And if you change one little implementation detail of a function, you're going to break a whole bunch of tests. That's typically why unit tests are okay to be white box, as in break abstraction, because if you change the implementation of a function, in theory, the worst case thing that's going to happen is that you're going to ruin the unit tests on that function, and that's it. In terms of this testing in the large, there are 3 general categories that you could put these in, and these aren't biblical to written down, because it depends on the software system. Some software systems are so small that you couldn't even break the size of it up into 3 tiers. Like your project could maybe be broken up into 2, probably, maybe 3, or they blend together. So if you look at the bottom here, what we're saying is that when you look at testing many things, you could either do it via module, which I would think about typically as, say, a file. You might have a file with a few functions in it. So you could think about that as a module with a few units in it. You then might have your integration tests, which are testing how all these different modules fit together. So are you testing how different files like auth.py and channels.py interact with each other? And then you have system tests, which test the entire system, everything. Now here's the thing for your project, right? The reason I say you don't have to get too worried about the distinction between these is that for your project, obviously you have a sense of modules, right? And obviously you have a sense of, integration tests, which is not just testing within a module, but between elements of a module, but testing between modules, like between files. But system tests, testing the entire system, well, you're kind of testing the entire system already. So the distinction between integration tests and system tests here is not that big. Like for your project, you kind of just have maybe some module tests, which aren't really tests you're writing per se. And you just have integration tests testing between modules. And in that way, most of the tests you're writing for your project fall into the integration tests category. Not all of them. We'll talk about some more after, but most of them fall into that category. Riley says, how do you unit test functions that depend on other functions? Do you use stub code, data storage? It's a great question. I'll answer that when we come back. Yeah, it's a good question. So that's testing in the large. It's testing how different pieces interact and see if they interact correctly. And then the last one we have, which I think takes us to the end of the lecture before I give some examples, is dynamic. It's acceptance testing. Testing that the software is actually, this is the highest level. Don't mistake this with validation, right? They can be easily mistaken, and naturally you could argue that there's some overlap between them, but acceptance testing is kind of the highest level of abstraction you can look at when it comes to a system. So let's say for a second, I'll give you some concrete examples in a sec, but let's start with acceptance testing. So if you build a UNSW Streams app, right, and you write some unit tests for functions, you do your integration tests like you're doing for iteration 1, where you have all these different tests, and then you're done and you say, I've done all my integration or system tests, let's do some acceptance testing. And what some acceptance testing would be is actually taking your software to an actual person sometimes, like a customer or a user or a stakeholder, and actually letting them use it and giving them a checklist of things. So this isn't really validation where we say, does this solve your problem? Was the right software built? That's kind of, maybe another step. It could be combined, but think of that as another step. This is the software built right, but we're not using PyTest, we're not using engineers, we're actually using people to look at it. So this is true for a lot of big companies, right? Like let's take, what's a big B2B company? Because it tends to happen with, B2B companies or something. Like often when you're building software, and we'll talk about this when we talk about deployment, you will write software, you'll test it, you'll do that whole continuous integration thing, which is often your unit tests and your integration tests. And when you're ready to say, publish the software or make it available, you tend to actually put it through an interim stage where people actually use it in its entirety, in like a test mode. I mean, Mason, he says, is this basically like playtesting for games? Yeah, I mean, it is. But the questions you're asked, like, but the thing is, it's not so much like you're giving a game to someone and saying, oh, can you test if you like this? Because that's kind of validation. That's actually testing if you built the right game sometimes. It's actually like, here's a game. We want you to, jump, walk forward, pull out your axe. Sorry, what is it? Did anyone ever play Ratchet and Clank? Or is this definitely one of those, I'm unambiguously 8 or 9 years older than you? No, ever play this on PlayStation? It's a fun game. Anyway, I don't know why, but he had a big spanner thing. Okay. Yeah, it's like, so you give someone this game, it's like, what is an acceptance test? It's like, well, the engineers have unit tested the software, they've done all their integration system tests together, and now they're giving it to you, and they've given you a checklist, and they say to you, PS5, oh wow, this game really lasted a long time. I didn't think they were still making them. There you go. Alright. Well, that's nice that it didn't die. It's like, so you give this to someone like you, and you say again, can you jump? And they jump. Okay, and you're like, check. Then you're like, can you pull out the ratchet? Ratchet? No, what is that? The spanner? I don't know. Never named that before. And they check that, and you say, can you, jump? You check that, and you say, if you click this, does the menu come up? And you check that. It's literally the highest level of abstraction following some kind of checklist. And often it's done internally, or it's done by like stakeholders, or you mentioned open beta, early access, all of these things. It's a test bed to actually make sure that your software is doing what it should, that the system has been built right. My stream is being a bit unstable at the moment, so sorry if it buffers for a bit. As I mentioned yesterday, I'm getting NBN tomorrow, so no more stream issues. Hopefully. So that's acceptance testing. Super simple. It's very easy to conceptualize, I think. Then validation would come after that, and that's actually where you might ask yourself, okay, well, this game was designed to, for people to have this much fun with it. They should want to play it for 3 hours. They should feel this way when they play it. Did this game actually do that? If the answer is yes, then it's like, okay, well, good. We validated that, we built the right software. So working backwards to the start, back to testing in the large. So I got the hiccups. I won't go into this in much depth because I think this is the one that you have a tactile understanding of, given that it's what you're doing for your project, right? You understand that it's black box. You understand that you have these different units or these different modules or these different files, and you have to just test them together. So in your project, you're probably doing something like running auth register. Okay, and then you run channels create, and then you get channels details. You're integrating how different pieces of software work. So this is a form of testing in the large. The real kind of interesting question, though, is like, what is testing in the small? What is a unit test? And there was a great question earlier that was like from Riley, which was, how do you unit test functions that depend on other functions? Do you use stub code or data storage? And the answer is yes, typically. So like if we go to the project, so I maybe just think for a second, if you start with this and you say, I'm not doing unit tests in this project, you might have a better place to start. So what I'm doing is I'm going to go grab my branch here where we implemented some stuff. And we implemented auth register, right? Or maybe let me clone this. We'll do this for like 5 or 6 minutes, and hopefully I'll drive the point home a little bit on unit tests. Then we'll take a break at like 10:05 or something. Then we'll go through code coverage. We won't talk about like next week's stuff today. Okay, so if I just clone project here, this is like the course project, so it's not really like your project. So if I come here and I go to my iteration 1 branch, and I open up my code. Great. And what I've got here is I've got 2 important files that we saw last time, right? I've got my auth test, and I've got my auth.py. Now, This is from the iteration 1 introductory video, and you know, on the odd chance people are looking at this when we have a different project for some reason, it's obviously going to be a different project, but this is our auth register function. And we implemented it and we wrote some tests for it. And what you've probably noticed if you've done part of the project is that to write tests for some functions like register, most of the way you're probably testing it is by registering it, assuming it works, and then using that information later. And there's actually not a ton you can test. You can definitely test if errors are thrown, but how do you know that the data it returned is right? How do you know that it actually behaves? So this you could technically classify as a unit test. Maybe that's one thing I want to start with. As well as this one, as well as this one. And that's because they're just testing a function. They happen to be a black box unit test because that's how the course is mandated you do your tests. However, that doesn't mean that it's the only type of, like, you could call this a really simple integration test. You know, there's no like hard lines when it comes to testing, right? Like, you could be like, yes, this is the beginning of my integration test, or you could say this is a black box unit test. Both of those things are kind of true. It's not actually testing things integrating, so it's probably like not literally an integration test. It's probably a unit test because it's just testing a unit. It's just testing this function. However, testing black box, just a function, is really hard. Like, how do you even test channels create without auth register? Because we've told you, like, you have to write your test before you implement. That's why, again, integration tests are often black box and stuff like this. With unit tests, though, it's okay to write some white box tests. And just to be clear, this is not what we're asking you to do in the project. You know, it's just how we made a choice. It's not something we're interested in. But how would you write a white box test for auth register? Well, to write a white box test, you can break abstraction, which means break through the abstraction layer and actually start digging around with the code. So, like, what do you know about when you register a user? Well, let's do one here. So if we write a test called test register white box, where we'll clear the data store, and then the first thing we might do is we might actually import the data store now. So just to be clear, this is white box testing. This is not what you should be doing in your project. And then you'll get the data store. You say store equals data store.get. Okay, so you get it. And now you're going to assert that the structure of the data store is what you expect, which is that you want to assert that store users is an empty list. So this is white box. You're actually testing the specific details of the implementation. Then what you might do is you might auth register with, say, a valid user, you know, hayden@unsw.edu.au. And now you might actually assert again that store users is now actually going to be a list with one item in it. You know, and that item is just going to be a tuple with ID 1 and this email address. So, like, what's the ups and downs of a white box test? Well, the ups are that it's much more thorough because you're actually making sure the code didn't accidentally pass. Because a black box test, the code could be broken, but because you're looking at a high level of abstraction, it might just accidentally work, even though it's doing the wrong thing under the hood. The downside of a white box test is that it takes more time to write. It also makes your code more not durable, because if someone comes along and says, oh, the data store is terrible, let's use a database or something like this, you have to go and rewrite all your white box tests. But with black box tests, the entire rewriting of an implementation should still let your black box test pass. That's why it's generally like good programming practice. But that's an example of a white box test. And this is an example of a unit test as well. Obviously, if you were to test more functions, it would be like a white box integration test or a white box large test. But again, that's just not too common because they become very brittle tests. So again, just to recap, white box unit test, black box unit test, large tests, which might be like it's large integration tests, either like integrating units within a file, integrating units between files, or integrating every unit. So to go back to some questions here, because we're kind of at the end now, and in fact that was really the end of that, so I might just pull up the feedback slide while I answer some questions and before we take a break. Waleed says, so instead of pieces of code or engineers testing it's doing what it's supposed to do, users test that. But they don't have to test whether it was they don't have to test whether that thing was the right to do in the first place. Yeah, so the way I think about it and have described it is that, you know, validation is actually sitting down with stakeholders and saying, does this solve your problem? Did we get the solution right? You know, and verification sitting down with, you know, users or stakeholders sometimes, or, you know, testers or external testers, and just saying, this is our solution. Here's how we've defined if we built it correctly. You're going to come at this with a really, really high level of abstraction, like literally say playing the game or using the website. Can you just check these things off for us? Tell us if we actually passed all these things. But yeah, you're on the money with that. Izzy says, I think with Zelda Breath of the Wild, one test they had, not sure if this counts, was that they gave the game to some people on the team and were told to explore, and they tracked what areas were least visited. That's interesting. I mean, that's super interesting, because like I don't even know if I would call that specifically verification. I mean, that's what you would typically maybe call research or something. That's good practice. I don't really know what label I'd give it in the context of what we're doing here. But that's super cool. And like, that's becoming something that's like a lot more potent these days in software in general, is just more research and more data analytics. And examples of that as well are, like you mentioned, like Zelda Breath of the Wild. It's like, it's not even just like nowadays they don't just sit, I'm not saying for Zelda games specifically, but they don't just sit people down and monitor them. Nowadays they'll actually collect this data at large. Like, you know, you could design games now that are constantly sending data back to a server and collecting that information at scale, you know? Like Google and other companies do this. They literally look at where, I mean, I don't want to pick on Google, but it's just like lots of companies do this. They literally look at where your mouse is on the screen, and they aggregate all that data, and they say, wow, this part of the website's not being used very much. But that's a separate topic to anything today. It's interesting though. Can we use other functions in our tests for a specific function? Yes. If you use multiple functions or multiple units, it becomes a kind of integration test. So that's absolutely what you have to do. When Quinn says, is the data structure of data store customized by each group? Yes, it's totally up to the group. Naturally, it could be a lot of them will probably be very similar. Blake says, is it okay to have white box tests that aren't included in master branch? Yeah, like, I don't care. Like, we're going to mark master. Your tutor's not going to be craving marking more of your work. Like, they're going to mark master, nothing more, nothing less. Will we be deducted marks for white box testing? Look, so the short story here is don't put white box tests in your master branch. I don't even think you need to write them, frankly. I wouldn't write them if I were you. You can. That's totally fine. Good on you for being thorough. But don't put them in master, because it's going to confuse your tutor into thinking that you don't know what the hell you're doing. And if you really want it in master, talk to your tutor at least, so that you've told them that. And then when they go to mark you, they're like, oh, this group was aware these were not the tests that should be written. But I wouldn't keep them in your master branch. I think what I've actually been telling groups is that if you want to do white box testing for some reason, then that's fine. But, and this is a really big but, don't put it in your tests folder. Make another folder called like test white box or something. Like, put it in another folder, because it's just like, if we do decide to do some extra checks or marking on this, we might just test everything in your test folder, and don't have bad stuff in there. So just short story, don't have your test folder is what we mark for tests. Make sure there's all the right stuff in there. You can put it in another folder, you can put it on another branch. I'd still recommend talking to your tutor. Is it alright if we white box test for channel messages, since we can't really feasibly black box it? We don't even expect, like, yes, you can do that. But again, black box testing has its limits. We don't expect you to break beyond those limits in this course. But if you want the personal confidence, then feel free to. Diorora says, what if the inputs for multiple functions result in additional errors being raised? How can we catch both sets? You can only catch one error at a time. You don't need to worry about two errors being caught or anything like that. Spark says, if we have a helper function that do things like create channel, update user, etc., do we need to show a white box test, or do we need to show tests at all? You don't need to test helper functions. Like, you have to understand again that these are abstractions. So, you know, if you have your auth register function, your auth login function, your channels create function, if you write helpers, they're typically underneath here helping it out. And what a black box test looks at is it says, we're not going to look underneath the interface. So like if you have helpers, we don't expect you to test those helpers in this iteration, right? You can test them black box, you can test them white box, like it doesn't really matter, but it's like all we're interested in is that you write tests that just use the interface. That's what we expect from you. If you need to take that further or you want to take that further, you can. Most groups do not. The only thing again I'm saying is if you are writing tests that are not compliant with what we've asked for, which is black box tests, put them in another folder. How do you test for a success without direct access to the data store? I'll really reiterate this again. Black box testing has its limitations, right? You can't test everything. The more abstractions you have, the less certainty you have that the specific underlying mechanics are working. It's just physics, right? Not literally physics. So we have a line in the spec which I added and is really important, which I think is 6.2, 3, 4, 6, 7, 8, I don't know. 6.4? Sparse. I think I said sparse. Yeah. 6.5. Testing. A common question, how can I test this or can I test this? In any situation, most things can be tested thoroughly. However, some things can only be tested sparsely, as in they can only be tested to an extent. And in some other rare occasions, some things can't be tested at all. A challenge of this project is for you to figure out which is which. So your questions around, how do you test success without direct access to a data store? What I'd say to you is there's not something we haven't taught you that allows you to do that. We've taught you everything we know about testing. Like, it's not actually, testing is a pretty simple concept. And some things you can't test, talk to your group, figure out, we definitely think that one is one that's just not possible to test, right? Maybe you'll get them all right, maybe you'll get them all wrong. That's the fun of education and learning and feedback and stuff. And Blake says, if they can't be tested, does that mean you won't test them in marking? Yes, because we can't test them. There are some things we literally couldn't test. There are some things you could technically not do or implement that are not able to be verified via black box testing that we just won't be able to tell if you've done or not. That's the limitation of black box testing. So we can only test what you can test. Like, we're both working on the same set of rules of engagement here. Last question, we're going to take a break. Eric says, since black box testing is limited, is there like a minimum number of tests we need? Oh, look, I mean, it depends what's in your test, but, it depends how many asserts you have in your tests. It depends how you structure them. I don't want to give you a number. I'll give you like a rough number because I know everyone wants a number, but like you should be able to write thorough tests for your code in 20 to 100 tests. I know that's a BS answer, but it's true. Like, some people will write it very well, very thoroughly. Some people will write it just enough. I mean, you've got like 12 functions. You should be able to write at least 12 tests. Many of them, you'd have many tests, right? Like auth register, you've got invalid names, you've got invalid emails, you've got invalid passwords. There's like 3 already. Anyway, let's take a break. This is the end of 3.4. Thank you.